Hello everyone. This is Katsutoshi Itoyama from Tokyo Institute of Technology. I'm going to start practice 3 of Hack tutorial. This is the contents of practice 3. In practice 3.1, we introduce distributed processing using Hack loss. In practice 3.2, as an example of more practical distributed processing, a robot simulator called Turtle Sim is controlled using sound source localization. In practice 3.3, we introduce distributed processing using Mqtt instead of loss. In practice 3.4, we introduce compressed transmission of acoustic signals using HackCN. Okay, then we start from practice 3.1, distributed processing using Hack loss. First, I will explain about loss. Loss is middleware widely used for research and development of robots on heterogeneous computer clusters. Although the name includes operating system, it is not an actual operating system like Windows or Mac. In loss programming, robots, sensors, and controllers are represented as nodes and are connected by a messaging bus topic, as if it were a graph structure. According to the publish-subscribe messaging model, nodes send and receive messages, such as sensor measurements and motor currents. Then, I will explain about the concepts of Hack loss. One is to utilize Hack audio functionality from loss, such as source localization, separation, and recognition functions. These functions are provided as frame-based processing, that is, processing at fixed time intervals, which loss is not good at. The other is to utilize loss functions from Hack, such as motion and vision processing, recording and playing back various types of data, and event-based processing. With Hack loss, Hack functions networks can be made into loss nodes. Overview of Practice 3.1. A sound source localization system similar to the one constructed in Practice 1 is realized by distributed processing using Hack loss. The entire sound source localization system is represented by a loss network consisting of two nodes. The first node has the name Hack master node A. It reads the audio signal, then performs Fourier transform and localizes the sound sources by music, and then publishes the result to the topic named Hack source. The other node has the name Hack master node B and subscribes to localization results, tracks sound sources, and displays the results. Now let's actually run this system. The first step is starting loss core. It needs to be started before any other node. Open a terminal and type loss core. Then, log messages shown on the slide will be displayed. Note that only one loss core can be started in a loss network, even for distributed processing using multiple computers. The next step is starting the publish and subscribe networks as loss nodes. Open two new terminals. It's convenient to press Ctrl-Shift-T twice to open them in tabs. In the first new terminal, start the network that subscribes to localization results. In the other terminal, start the network that publishes localization results. Please add two arguments, audio file and transfer function. The final step is to check the localization results. The localization results are shown in the window as shown on here. As an optional step, you can see the nodes and topics on the loss network. Open a terminal while sound source localization is in progress and type RQT graph. You can see that the two nodes are communicating by the topic named hack source. This is a network diagram of publisher node. Like practice 1, it consists of a main seed and a loop 0 iterator. Loop 0 uses a node called loss hack messages publisher. Since the sound source localization will be published, connect the output terminal of localized music to source info terminal of loss hack messages publisher. On the main seed, place a node called loss node generator. This node allows the network to act as a loss node. Loss node generator gives the name of the node. Please be careful not to conflict the name with other node. This is a network diagram of subscriber node. Like publisher, loop 0 iterator uses hack messages stream from loss node. Please connect the source out terminal of this node to input terminal of source tracker. Loss node generator node is also placed in main seed of this network. We will proceed practice 3-2, controlling turtle theme using source localization. I will explain about turtle theme. Turtle theme is a standard tool widely used for teaching loss. You can operate a turtle that imitates a robot in a 2D virtual environment. The commands that can be sent to the turtle are the same as those used in real robots, such as forward, backward, rotation, and so on. So it is easy to apply to real robots, such as TurtleBot. The goals of this practice: one is to display a turtle in the direction of source. The turtle, the brown one in this animation, it follows the movement of the sound source. If multiple sources are detected simultaneously, only the latest source is shown. The other is to move another turtle, the green one in this animation, towards the turtle of the sound source. This is the loss graph diagram. Three nodes are used: hack master node, hack tutorial node, and turtle theme node. Hack master node performs the sound source localization and publishes the localization result. The hack tutorial node displays the first turtle at the position corresponding to the sound source direction. It also publishes a command to move the second turtle towards the first turtle. The turtle theme node simulates the movement of a turtle in response to a received command in a 2D environment. Now let's actually run this system. The first step is starting loss score if stopped. You don't need anything if loss score keeps running. The next step is starting 3 loss nodes. Open 3 new terminals. In the first terminal, start the turtle theme node. Please type loss run turtle theme underscore node. In the second terminal, start hack tutorial node. Go to this directory, type python3 and lossturtle.py. In the third terminal, start hack master node. Go to the same directory and type hackmw practice3.2.m with wow file and transfer function. The final step is to check the results. We prepared two WAV files. The one is around.wav and the other is rape.wav. In around.wav, the source moves around the microphone array, as shown here. In rape.wav, the sound source rapes every 90 degrees. Rape, rape, and rape. You can see the difference of the source positions and the trail of the chasing turtle. This is the Hack network diagram of Hack master node. Actually, this is basically the same as the previous practices. Functions related to displaying and moving turtles are written in Python script. I will avoid explaining the entire source code, but I will explain the important parts. The part shown on this slide describes the function to display the turtle according to the direction of the sound source. The first block is for displaying only the turtles that correspond to the latest sound source. The sound source ID assigned by Hack is used in this part. The next block calculates the coordinates and angles of the turtle according to the source direction by using this sine and cosine function and so on. This block is a processing when a new sound source appears. The old sound source turtle is removed by this kill function, and the new sound source turtle is displayed by this spawn function. The last block is the processing for continuously displaying the existing sound source by using this teleport function. The Python script on this page implements a function to move the second turtle that tracks the first sound source turtle. The first block is a constructor of the object that implements the function. losspy.subscriber is a method for registering a function, self.callback, to be executed every time a specific topic is received in the loss node. The topic to subscribe to is /turtle1/pause. That is the current position angle and angle of the tracking turtle. The type of data is pause. At the same time, we use losspy.publisher function method to register the topic published from this loss node. That means the name of topic is /turtle1/command velocity and the data type is twist, which is one of predefined data types on loss. The next block defines a self-callback function, which will be executed when the topic is received. This function copies the coordinates and angles from the received data into the field of the object itself. The last block is a function that creates a move command to the tracking turtle. Here creates a velocity and turn angles towards the source turtle and then publish the command. The Python script on this page implements a function when sound sources are found. The first block is the constructor of the object that implements the function. As same as the previous page, using the losspy.subscriber method, the name of the topic, the date type, and the function handler are registered. In addition, we create two turtle objects. One is to track the sound source, turtle move, and the other is to display the source, turtle source. The next block defines a procedure when sound source is found. For each sound source contains the received data, the turtle is displayed according to the sound source direction, and the move command is sent to the tracking turtle. The Python script on this page describes the initialization process for system operation. The first block initializes loss node with name using losspy.init_node method. The second block resets the TurtleShim virtual environment. The third block registers the publisher and subscriber to this loss node. The final block, losspy.spin method. This method prevents terminating this Python script and keeps the callback function running. Then we proceed to Practice 3, distributed processing using Mqtt. I will explain about Mqtt. Mqtt stands for Message Querying Telemetry Transport. Mqtt is a lightweight network protocol commonly used in IoT devices with low computing power and unstable networks. You probably know HTTP and HTTPS. These are network protocols widely used in web services. Mqtt is one of the similar network protocols, but it is designed to be more lightweight than HTTP and HTTPS. Mqtt uses publish and subscribe messaging model like ROS. And in MQTT, a broker service like ROSCore in ROS delivers messages. Mqtt have several functions to enhance stability, such as quality of service QoS, and will and retain, and so on. This is an overview of Practice 3.3. A sound source localization system similar to the one constructed in Practice 1 and Practice 3.1 is realized by distributed processing using Mqtt. The entire sound source localization system is represented by an Mqtt network consisting of two nodes. The first node reads the audio signal, performs Fourier transform, and localizes the sound source by music, tracks sound sources, and publishes the result to the topic name hark/data/sources. The other node subscribes the source tracking results and displays the localization results. Now, let's actually run this system. The first step is starting an Mqtt broker, Mosquito. It needs to be started before any other node, like loscore. Open a terminal and type Mosquito. Then log messages shown on this slide will be displayed. Actually, the distributed virtual machine will start Mosquito automatically, so you may just check the above error message. The next step is starting the publish and subscribe networks at Mqtt nodes. Open two terminals. In the first terminal, start the network that subscribes to localization results. The name of network file is practice3 sub.n. In the other terminal, start the network that publishes localization results. The name of network is practice3 pub.n. With two arguments, the one is audio file, the other is transfer function. And then you can check the localization result as shown here. This is a network diagram of publisher node. Like practice 3.1, it consists of a main seed and loop 0 iterator. Loop 0 uses a PyCode executor 3 node, which enables to execute a Python script. The executed Python script is shown below. Practice3 pub.py. In the first block of this script, this is initialization procedure of an Mqtt client. It specifies the Mqtt broker host, localhost, and its port number. In the rest blocks, these are the procedures to publish the localization results. Data from sources input terminal is serialized to JSON format and then published to topic hack/data/sources. Actually, Hack does not have an API to handle Mqtt natively. Therefore, communication using Mqtt is realized by using a Python script executed via PyCode executor 3 node. This is a network diagram of subscriber node. As same as the previous slide, PyCode executor 3 is used. The executed Python script is shown here. The important part in this script is here, onMessage method. This method will be executed every time receiving Mqtt topic. In this method, the received data is deserialized from JSON format and stored. This is the rest part of Python script. This calculate method here will be executed every 0.01 second intervals by using here this time.sweep method. In this method, the type of the received data is checked because Mqtt allows any kind of data format. So if the received data is not related to the source localization result, this method do nothing. Only if the received data format is related to the source localization information, this method outputs the source information. If the data type is appropriate here, then the data will be output. Okay, then we proceed to practice 3-4, compressed audio signal transmission. This is the final part in this practice. In this practice, let us imagine the situation where the audio signal itself is transmitted through Mqtt using FLAC free lossless audio codec compression. So this is a network diagram, very simple network, just reading the audio signal, transmit by FLAC compression, and save audio signal. If we use FLAC compression, the data transfer speed is about 500 to 600 kilobytes per sec using FLAC compression. On the other hand, the data transfer is more than 2000 kilobytes per sec if we do not use FLAC compression. The data reduction is very effective to enhance the stability of the system under unstable networks. The first step is starting an Mqtt broker, Mosquito. It is the same as the previous practice. The second step is starting subscriber and publisher networks. Open two terminals. First is start the subscriber network. The name of network file is practice34sub.n. And then start the publisher network. The network name is practice34pub.n with audio file. Note that the current version of this network support only 8-channel audio signals. Actually, this 8-channel is specified by the parameter in this network file, can be transferred. And this subscriber network outputs the received audio signal. It is saved in rec_0.wav, this file. And this is the network diagram of publisher network. This network contains two seeds, main seed and loop 0 iterator. Loop 0 has very simple structure, just audio stream from web node and then publisher FLAC node. This node reads from audio signal from waveform file, and then this node publish the audio signal by compressing the FLAC into FLAC format. In this node, the number of channels must be specified here, and the Mqtt, the host and port of the Mqtt broker must be specified here. And this is the network diagram of subscriber node. This network has two seeds, main seed and loop 0 iterator. In the loop 0 iterator, the subscriber FLAC node and save web PCM node are pressed. And this subscriber FLAC node receives the FLAC compressed audio signals via Mqtt protocol. And in this node, the host name and port of the Mqtt broker must be specified as same as the previous page. And this save web PCM node outputs the received audio signal into waveform files. Okay, this is the end of this practice 3. Thank you for listening.